Have you ever wondered what actually happens when you run a Python script? Like, really happens. You write some code, you type python main.py, you hit enter, and stuff just appears on the screen. Today we're going under the hood of Python itself. We're going to look at the bytecode your code gets compiled to, the virtual machine that executes it, and the famous, or maybe infamous, global interpreter lock. And I promise, by the end of this video you will never look at a Python program the same way again. Alright, so let's start with something embarrassingly simple. I'm going to write a tiny function called total price. It takes a price and a tax rate, it computes the tax, and it returns the price plus that tax. This is about as basic as Python gets, and that's exactly the point. Now let's actually call it. I'll print total price of 100 with a 20% tax rate. And let's run this thing and see what happens. Okay, 120. No surprises there. But here's the thing. Between the moment you pressed enter and the moment that number showed up, an entire hidden machine did a ton of work. And that machine is what this video is all about. So let me draw out the big picture for you. Everything starts with your source file, main.py. And here's the first thing to realize. That file is just text. It's characters in a file. Your CPU has absolutely no idea what def or return means. Nobody can execute text directly. So the very first thing Python does when you hit enter is it hands your file to a compiler. And yes, I said compiler. Python has a compiler built right in. It parses your text into a syntax tree, checks that everything is valid, and then compiles it. Not to machine code like C or Rust would, but to something in between. That something is called bytecode. Bytecode is a compact, low-level set of instructions. Things like, load this variable, multiply the top two values, return the result. It's not tied to your CPU at all. It's designed for a made-up machine, a virtual machine. And that's the last box, the Python virtual machine. At its heart, it's a giant loop written in C. It grabs one bytecode instruction, executes it, grabs the next one, executes that, over and over, millions of times a second. That loop is what's actually running your program. So when people say Python is an interpreted language, this is what they really mean. Your code is compiled, just like the fancy languages. It's just compiled to bytecode, and then a virtual machine interprets that bytecode. Both things are true at the same time. Keep this picture in your head, because now we're going to prove every single box in it. And actually, you've probably already seen proof of this compile step without realizing it. Let me show you. I'm going to ask Python to compile our file explicitly, using the compile-all module. And now, if we look inside the PyCache folder that just appeared, there it is. main.python311.pyc. 375 bytes of pure bytecode, sitting right there on disk. That mysterious PyCache folder that shows up in every Python project you've ever touched? It's literally a cache of compiled bytecode. Python saves it so that next time you import this module, it can skip the compile step entirely and just load the bytecode. That's why second imports feel faster. Okay, but I don't want to just stare at a file listing. I want to crack a function open and look at the actual bytecode inside. So let's create a new file. I'm calling it bytecodelab.py, and let's do some exploring. Now, here's something most people don't know. Every function you define in Python carries its compiled bytecode around with it, at runtime, on an attribute called $code. So I can just grab it like this. And this code object is a real, inspectable thing. Let's print a few pieces of it. First, code, the raw bytecode bytes themselves. I'll take the first 16. Then consts, the constants the function uses. And varnams, its local variable names. Alright, moment of truth. Let's run the lab and see what a function actually looks like on the inside. Okay, a couple of things here. First, you see that 120 at the top? That's because importing main actually executed its print statement. Classic Python gotcha, imports run code. But look at the second line. That byte string right there, that is your function. Those raw bytes are the compiled instructions the virtual machine will execute. And below it, the supporting cast. The constants tuple just holds none, and the variable names are price, tax rate, and tax, exactly the three locals our function uses. The bytecode refers to these by index, not by name. That's part of why it's fast. Now obviously, raw bytes are not exactly readable. Luckily, Python ships with a disassembler in the standard library. It's the dis module we imported at the top. So let's add one more line, dis.dis of total price, and run this again. And there it is. This is your function, disassembled into human-readable bytecode. Every line is one instruction for the virtual machine. On the left, you've got the source line number, then the instruction's position, then the instruction name, and its argument. I'm on Python 3.11 here, by the way. The exact opcodes change a bit between versions. Look at line 2 of our source, tax equals price times tax rate. It became 4 instructions. Load fast price, load fast tax rate, binary op multiply, and store fast tax. And our return line became load, add, return value. Simple, mechanical, one source line at a time. But to really read this stuff, you need one mental model. The Python virtual machine is a stack machine. There are no registers like a real CPU. There's just a stack of values, and every single instruction either pushes something onto it or pops something off of it. Let me draw what that multiplication actually looks like. So load fast price. All this does is take the local variable price, in our case 100, and push it onto the stack. Load fast is called fast because it grabs the variable by a numeric index, slot 0, no dictionary lookup, no searching. Then load fast tax rate does the exact same thing with slot 1. So now the stack holds two values, 100 and 0.2, sitting right on top of it. And now binary op multiply. This one pops both values off the stack, multiplies them, and pushes the result, 20, back on. That's it. That's the whole trick. Finally, store fast takes that 20 off the stack and stores it into slot 2, the tax variable. Push, operate, pop. Every Python expression you have ever written, no matter how complicated, breaks down into exactly this dance. Once you see it, you can disassemble any function in any codebase and actually understand what you're looking at. Okay, so far so good. But remember that giant C loop I mentioned, the one executing instructions one by one? There's a detail about that loop that has caused more arguments in the Python community than anything else. The global interpreter lock. And instead of just telling you about it, I want you to watch it happen live with a timer. Here's the experiment. I've got a function called countdown that just decrements a number until it hits 0. Pure CPU work, no files, no network, nothing to wait for. And n is 50 million, so this takes a couple of seconds. First, the baseline. I'll count down all 50 million on a single thread and time it with perf counter. And now the interesting part. I'll split the exact same work across 2 threads, 25 million each, start them both, and wait for both to finish. Now, if threads actually ran in parallel, this should take roughly half the time, right? That's the whole promise of threads. All right, let's run it. This is a real benchmark, so it'll take a few seconds. The single-threaded version is crunching first. There it is, about 2.6 seconds. And now both threads are running. And look at that. 2 threads. The same 2.5 seconds. We doubled the workers and gained absolutely nothing on a machine with plenty of idle cores. So what is going on here? This, right here, is the global interpreter lock in action. Let me draw it. Here's the deal. Both of our threads are real operating system threads. But inside CPython there is one single lock, the GIL. And the rule is brutal. A thread must hold that lock to execute Python bytecode. Any bytecode. At all. So only one thread can be inside that big interpreter loop at any moment. Thread 1 runs for a few milliseconds, releases the lock. Thread 2 grabs it, runs a bit, gives it back. They're not running in parallel at all. They're taking turns, really fast. For CPU-bound work, threads in Python are basically an elaborate illusion. Now, why would Python do this to us? It's not malice. The GIL makes Python's memory management, which counts references to every object, simple and fast for single-threaded code. And it means one thread can't corrupt an object while another one is halfway through modifying it. It's a trade-off, and honestly, for most programs, it's a pretty reasonable one. But what if you genuinely need all your cores? Well, here's the classic escape hatch. Let me rewrite the same benchmark with multiprocessing instead of threading. Same countdown, same 50 million, but now each worker is a full separate process. Each process gets its own Python interpreter, its own memory, and crucially, its own GIL. So there's nothing to fight over anymore. Let's run it. And there we go. 1.5 seconds instead of 2.6. That's a real speed up from actually using 2 cores at once. Now, before you go rip threading out of every codebase you own, hold on. Because here's the part people get wrong in the other direction. The GIL only hurts CPU-bound code. If your threads spend their time waiting on network requests, on database queries, on reading files, Python releases the GIL while they wait. So a web scraper hitting 50 URLs with threads? Massive speedup, completely real. Threads waiting on input-output overlap beautifully, because while one thread waits for the network, another one holds the GIL and does work. That's why the rule of thumb is threads for waiting, processes for computing. Also worth knowing, libraries like NumPy release the GIL inside their heavy C loops, which is one more reason vectorized code runs circles around plain Python loops. And the story is still evolving. Python 3.13 shipped an experimental free-threaded build with the GIL completely removed. It's not the default yet, but the era of the GIL is slowly coming to an end. One last practical nugget from the bytecode world. Remember load fast with its numbered slots? That only works for local variables. Globals go through a slower lookup called load global, which means the exact same expression is measurably faster inside a function than at the top level of your script. So when someone tells you to put your hot loop inside a function, this is why. It's not superstition, it's bytecode. All right, let's zoom back out, because you now know the whole machine. Your source code gets compiled to bytecode and cached in PyCache. That bytecode runs on a stack-based virtual machine that you can inspect anytime with the dis module. And that virtual machine runs one thread at a time because of the GIL, which is exactly why threads are for waiting and processes are for computing. Next time somebody dismisses Python as just an interpreted language, you can smile, pop open the dis module, and show them the compiler they didn't know they were using every single day. If you learned something today, a like genuinely helps the channel, and subscribe if you want more deep dives like this one. In the next video, we're using everything you learned today to make Python code dramatically faster, step by step, with the profiler open the whole time. I'll see you in that one.